In this question, we have Usain Bolt, who is starting at rest. He accelerates to his top speed, and eventually he completes the race maintaining that speed. So let us say that this is photo 1, which is just as he's starting the race. His velocity is 0, he isn't moving yet. Photo 2 is when he hits his stride and reaches his top speed. And photo 3 corresponds to when he finishes the race. I'm going to set the origin as his starting point. I'll set rightwards as being x. Now, let's write down all of the information that we know. Let's realize that we have now broken this motion into 2 distinct phases, and we need to. Why? Because he was accelerating between photo 1 and photo 2, but he was not accelerating between photo 2 and photo 3. He maintained the same velocity between photo 2 and photo 3. And that means that these are now 2 different regimes with 2 different accelerations. So that means we need 2 different sets of toolbox equations to solve them out. So in region 1 to 2 versus region 2 to 3, we're going to have to work with the displacement, the initial velocity, the final velocity, acceleration, and the time. So let's think about all of the things that are known in this story. We were told that it takes him 3 seconds to reach his stride between photo 1 and photo 2. And the remainder of the race was the total race was 9.69 seconds, which means that he spent 6.69 seconds in this second realm where he is not accelerating. And since the acceleration here is 0, we can also put that as a known quantity. Now, after that, we know that he started from rest, so his initial velocity in photo 1 is also 0. And that's all of the information that was actually given in the question. So you might be wondering, well, we only have 2 pieces of information in each one of these phases. So what do we do? The answer is we're going to do something like this. I'm going to create this variable, delta x 1 to 2, let's call it. I do not know how far he traveled between photo 1 and photo 2, but I do know how far he traveled from photo 1 to photo 3. It was a 100-meter dash. So that means that the total distance that he traveled was 100 meters. So if he traveled some distance, delta x, from 1 to 2, then he must have traveled 100 minus that between 2 to 3. Now, his velocity at photo 2 is unknown. So let's just call that Vf for the moment. But his final velocity in this phase, from between photo 1 and photo 2, must also be his initial velocity in the second phase. And since he isn't accelerating, that means that his final velocity in the second phase, that is at photo 3, must also be V final. We do not know what his acceleration was over here. But what we see is that there are really only 2 unknowns in this entire question. One is how far he moved between photo 1 and photo 2, and the other is what was his velocity at photo 2. What was his maximum velocity? In fact, now that I think about it, in order to make this a little bit clearer, I'm going to symbolize this as V sub m to represent maximum velocity. So let us apply toolbox equation 3 to each one of these. So the reason why I'm going with number 3 is because between 1 to 2 we don't know the acceleration, but I would like to set up a relationship between the displacement and the maximum velocity, and we can find the acceleration later on. So toolbox equation number 3 is the only one that doesn't use the acceleration. Toolbox equation 3 says that delta x divided by time is equal to V initial plus V final over 2. So for 1 to 2, that will be delta x 1 to 2 divided by the time, 3 seconds, is equal to V initial plus V final. That would be V max, all divided by 2. So if I were to simplify this, 0 plus V max is V max, and if I multiply both sides by 3, I'm going to get delta x 1 to 2 is equal to 3 over 2, or 1.5, times V max. What about from 2 to 3? From 2 to 3, we would say that the distance, or rather the displacement, that's 100 minus delta x 1 to 2, divided by the time, 6.69, is equal to initial velocity, that's V max, plus final velocity, which is also V max, divided by 2. So V max plus V max gives me 2 V max, but then dividing that by 2 will give me V max again. So multiplying both sides by 6.69 after all of that is done, I simplify that to 100 minus delta x 1 to 2 is equal to 6.69 times V max. Okay. So let's now take this equation over here and this equation over here, and let us combine them for delta x 1 to 2. That's going to give me 100 minus 1.5 Vmax is equal to 6.69 Vmax. Add 1.5 Vmax to both sides. That's going to give us 100 is equal to 8.29 Vmax. Is that correct? No, it should be 8.19. 0.19 Vmax. So now we can solve for Vmax. Vmax equals 100 divided by 8.19, which is 12.21 seconds. Sorry, 12.21 meters per second. And since we were doing everything in the x direction, this should be I hat. So this is something pretty clever that we've just done, isn't it? We did not know most of the information in the story, and yet by substituting things that we did not know together and eliminating them, we ended up with Vmax. How did we do it? We did it because I created two equations with two unknowns, and two equations with two unknowns can always be solved. Now that we have solved for Usain Bolt's maximum velocity, that was 12.21 I hat meters per second, we can now solve for all of the rest of the quantities over here, quite easily in fact. Let us say that we want to find delta x, that is delta x 1 to 2, the distance or the displacement that he experienced between photo 1 and photo 2. We can now use toolbox equation number 3 to solve for that. Delta x 1 to 2 divided by time 3 is equal to initial velocity 0 plus final velocity 12.21 divided by 2. So 12.21, 0 plus that will obviously be 12.21, divided by 2, and then multiplied by 3. And we find that the displacement that he experienced between photo 1 and photo 2 was 18.32 meters. And that would be in the I hat direction. Finally, we need to find the acceleration. We know initial velocity, we know final velocity, we know time. So the easiest way to solve for this would be using toolbox equation number 1. By the way, this was from 1 to 2, so I'll maintain that over here. Applying toolbox equation 1 to photographs 1 to 2, that is AT is equal to V final minus V initial, I would get A times T, that's 3, is equal to V final, which was 12.21, minus V initial, which is 0. So A is going to be 12.21 minus 0 is of course 0 divided by 3 gives us 4.07. 4.07 I hat meters per second squared. That was Usain Bolt's acceleration between photo 1 and photo 2. In this question, Usain Bolt is running a 200-meter race. Now, we're going to take a couple of photos over here. We're going to take one photo at the instant that he starts the race, a second photo at the instant where he reaches his stride and stops accelerating, and a third photo when he actually finishes the race. Why do we need 3 photos? Because there are 2 different accelerations here. He's accelerating from photo 1 to photo 2, but between photo 2 and photo 3, his acceleration is 0 because his velocity is constant. The toolbox equations only apply if you have constant acceleration. So where you have 2 different accelerations, we need to break the motion into 2 separate phases in order to solve. And that's precisely what we're going to do. I'm going to set this point where he starts the race as the origin. I'm going to set rightwards as being positive x. So we'll talk about photo 1 to 2 here, the first 2 photos, and from photo 2 to 3, we will talk about over here. Now, we were told that it takes him 3 seconds to reach his top speed, and it also takes him 19.3 seconds to run the whole race, which means that from 2 to 3, 16.3 seconds have elapsed. His acceleration from 2 to 3 is 0, and his initial velocity from 1 to 2 is also 0. His displacement from 1 to 2 I'm going to call delta x 1 to 2. And since this is a 200-meter race, I'm going to call his displacement from 2 to 3 200 minus delta x 1 to 2. His acceleration from 1 to 2 is unknown, but we do know that his final velocity for 1 to 2 is also going to be his maximum velocity for the entire race. Let's call this v sub m, Vmax. His final velocity for 1 to 2 is his initial velocity for 2 to 3, and because he's not accelerating, it's also his final velocity for 2 to 3. So, let's take all of this information together and solve for what that Vmax is. So let's apply toolbox equation 3 to phase 1 to 2, the first phase of motion between photos 1 to 2. We'll use that one because that's one where acceleration is not relevant. So toolbox equation 3 says that the displacement divided by the time is equal to V initial plus V final, all divided by 2. So if I were to simplify this, 0 plus Vmax is just Vmax. If I multiply both sides by 3, that gives me delta x from 1 to 2 is equal to 3 over 2 Vmax, which I can also write as 1.5 Vmax. So we will take this as our first equation relating to photos 1 to 2. What about from photo 2 to 3? Well, here the displacement is 200 minus delta x 1 to 2. The time is 16.3 is equal to, the initial velocity was Vmax, the final velocity is also Vmax, and we divide the whole thing by 2. Now, Vmax plus Vmax will give me 2 Vmax, but dividing by 2, I cancel that out, so I just end up with Vmax again. And then multiplying both sides by 16.3, I get 200 minus delta x 1 to 2 is equal to 16.3 Vmax. Now, I happen to know from this first equation that delta x 1 to 2 is equal to 1.5 Vmax. So let me take this and plug it in over here. 200 minus 1.5 Vmax is equal to 16.3 Vmax. Now, add 1.5 to both sides. I get 200 is equal to 17.8 Vmax. So now we can solve for Vmax. It is simply going to be 200 divided by 17.8, which is 11.24. So that is Usain Bolt's top speed in this race. Next, to find the acceleration of Usain Bolt from photo 1 to photo 2. From photo 1 to photo 2, we know that acceleration times time is equal to v final minus v initial. Now, the time required was 3 seconds, and that's going to be equal to 11.24 minus 0. So 11.24 minus 0 is, of course, 11.24, so we just need to divide by 3, and that'll give us 3.75. His acceleration is 3.75 I hat meters per second squared. And if we really wanted to, we could use all of this information that we have in 1 to 2, since we've now solved for his final velocity from 1 to 2, to figure out what his displacement was between photo 1 and photo 2. In this question, a person is throwing a rock upwards, and it is going to pass by a branch from a tree. It's going to reach its peak, and then it's going to fall back past the branch. So what we want to know is how much time elapses between the point where it crosses the branch the first time and the point where it crosses the branch the second time. But the question is rather devious in that it doesn't give you enough information between these 2 points. So it's clear that this point has to be one photo and this has to be another, but it does give you information about how it was thrown. So this photo will have to be photo 1. Where it crosses the branch the first time, that's photo 2, and where it crosses the branch the second time will be photo 3. I'm going to set upwards as the positive y direction and the point at which the rock started to be my origin. Now next, let us plug in all of the information that we know. There are now 2 phases, 1 to 2 and 2 to 3. Each one is going to have its own displacement, initial velocity, final velocity, acceleration, and time. So, after it leaves our hero's hand, it's going to be under the influence of gravity and gravity alone. So the acceleration is going to be negative 9.81 j hat meters per second, regardless of the two phases. We were also told that the distance from the rock to the branch in the first place was 7 meters, which also means that its displacement as it travels to the branch must also be 7 meters. Between positions 2 and 3, it has not moved at all in the y direction. Its y height has not altered between photo 3 and photo 2. It's at the same height in both cases. So that means that the displacement between those two photographs must be 0. Finally, we were told that it was launched at 15 meters per second upwards. That's positive 15 over here. And what we're looking for is this time, the time that elapses between photo 2 and photo 3. Now here's how we're going to go about solving it. We do not yet have enough information between photo 2 and photo 3 to solve for the time. But if we were to find the final velocity for 1 to 2, that would be the initial velocity for 2 to 3. So let's go ahead and do that. From 1 to 2, let's find the final velocity. We know delta y, we know v initial, we know a, we're looking for final velocity. There's only one equation that weaves together all 4 of those quantities and ignores time, and that would be v final squared minus v initial squared is equal to 2a delta y. So v final squared is unknown, but v initial was 15, and that's going to be equal to 2 times negative 9.81 times delta y, which is 7. Now, v final squared, 15 squared is 225, is going to be equal to 2 times 9.81, negative 9.81, times 7. So let's work that out. 2 times negative 9.81 times 7 is negative 137.34. Add 225 to both sides, you get 87.66. So v final from 1 to 2 is equal to 87.66, or more correctly, that's v final squared. And finally, we take the square root to get 9.36 meters per second. Cool. Now, we know the final velocity for 1 to 2, which is also the initial velocity from 2 to 3. So, we now have displacement, initial velocity, acceleration, and we're looking for time. The only equation that weaves together those 4 quantities is toolbox equation 3. Delta y is equal to v initial times t plus 1/2 at squared. So delta y was 0 is equal to v initial 9.36. In fact, I could just as well write it out over here. Times a time, which is unknown, plus 1/2 acceleration, negative 9.81, times time squared, which we don't know yet. Now, this equation can be simplified like this. 0 equals 9.36 t minus 4.905 t squared. You could solve this with the quadratic formula if you really wanted to, but that's just a lot more work than what's really needed. This equation is simple enough to solve by factoring. I can divide everything by t, and I can move this 4.905 t squared to the other side. That would give me 4.905 t is equal to 9.36. So 9.36 divided by 4.905 will give me 1.91 seconds. So the time that elapses between photo 2 when it reaches the branch the first time and photo 3 as it reaches the branch on the descending path is 1.91 seconds. In this question, we have a rock which is falling off of a cliff face, and if our hero is not careful, it will come and hit him on the head. Now, our hero does not see the rock initially when it falls, but he does see it 1.5 seconds later. So it's really from this point onwards that he has to get out of the way before it hits him in the head. So once again, this is a case where we have three different photos. One where the rock breaks off from the cliff. A second one when it is in mid-flight and when our hero sees it. And a third one which would correspond to when it putatively hits him in the head. So now we can break this question into two phases, 1 to 2 and 2 to 3. I'm going to set the level of his head to be the origin, and I will set upwards as being positive y. So we have delta y, we have initial velocity, we have final velocity, we have acceleration, and we have time. So the time that elapses between photo 1 and photo 2 was 1.5 seconds. The acceleration in both cases is negative 9.81 because it's falling under gravity, so negative 9.81 j hat meters per second squared. The initial velocity of the rock is 0. We do not know how far it falls from photo 1 to photo 2, but we do know that the total distance from photo 1 to photo 3 is 105 meters. So if we were to call this delta y 1 to 2, then this must be 105 minus delta y 1 to 2. Now, we have a lot of information in 1 to 2. So let's see what we can figure out so that we can carry it over to 2 to 3 and find out how much time elapses between when he first sees it and when it would putatively hit him in the head. Let's start by figuring out the displacement of the rock between photo 1 and photo 2. The way that we would do this is we would use delta y is equal to v initial times t plus half at squared, because that is the only equation that weaves together all four of these quantities. Delta y is the unknown, but it would be equal to 0 times t, 1.5, plus 1/2 times acceleration, negative 9.81, times t squared, 1.5 squared. Now, 0 times 1.5 is obviously 0, but the rest of this is going to simplify to negative 4.905 times 1.5 squared. So 4.905 times 1.5 squared is 11.03. So that means that the rock is going to descend by 11.03 j hat meters before our hero sees it. Now, because it has descended by this much, we can now figure out how much further it has to descend before it hits him in the head. Because I put this down as negative, I suppose I should put a positive over here. It's going to be 105 plus a negative number. So 105 minus this means it has still 93.96 meters to go. So that is delta y for part 2. Now the problem that we run into here is that we still don't have enough information to find out the time for phase 2. So what do? The answer is we have to find out the final velocity of the first phase, 1 to 2, and make that the initial velocity of 2 to 3. Let's go ahead and do that. So from 1 to 2, let us use toolbox equation 1. AT is equal to V final minus V initial. Negative 9.81 times 1.5 is equal to V final minus V initial, which was 0. So 1.5 times negative 9.81, that gives us negative 14.715. So the velocity at the end of phase 1 to 2, is also the initial velocity of 2 to 3. And we will treat the displacement from 2 to 3 as being negative because it's going against the y direction. I haven't been terribly rigorous about this in this question, so you'll have to forgive me on that. But now we have 3 pieces of information: delta y, v initial, acceleration, and we're looking for time. So from 2 to 3, we now have equation 2, toolbox equation 2 that we can use. And we can substitute in all the values that we know. Negative 93.96 equals negative 14.715 times the time, which is unknown, plus 1/2 times the acceleration, negative 9.81, times time squared. This is a quadratic equation, and we can rewrite it in standard form. So 1/2 times negative 9.81 will give us our usual negative 4.905. So we can rewrite it as negative 4.905 times t squared minus 14.715 t, and I can add 93.96 to both sides, is all equal to 0. Now we just need to solve for the time. To solve this quadratic equation, we would of course use the quadratic formula. We would say that t is going to be equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So the time is equal to negative b, which is negative 14.715, plus or minus the square root of b, negative 14.715, squared minus 4 times a, which is negative 4.905, times c, which is 93.96. And this whole thing is going to get divided by 2 times a, negative 4.905. So let's start simplifying this somewhat. Negative 14.905 squared is 216.531. So that minus 4 times negative 4.905 times 93.96 gives us 2060.02. So we get 14.715 plus or minus the square root of 2060.03, all divided by negative 9.81. The square root of 2060 is 45.39. So we now have t is equal to 14.715 minus 45.39 plus or minus divided by negative 9.81. Now if I added these, I would get a positive numerator, but a positive divided by a negative would give me a negative, so that won't work. instead I have to take the negative side. So 14.715 minus 45, and then divided by negative 9.81 gives us 3.13 seconds. So that is the time that our hero has after he sees the rock in photo 2 to get out of the way before it hits him in the head in photo 3. 3.13 seconds elapse between these two photos. In this question, there are 4 distinct photographs that are required. Here is the hot air balloon. Yeah, I know I made it look like a cupcake. You didn't come here because you were impressed with my drawing skills. So the hot air balloon is rising at 10 meters per second. And a ball is let go at this point. Now, because this is rising, the ball is initially going to have the same momentum as the hot air balloon. So it will initially rise as well until gravity takes it over and it starts to fall. Part of the question was asking what happens after 4 seconds. It will be somewhere in mid-air in the fall after 4 seconds. And eventually it's going to strike the ground. So in this story, we have 4 photographs, like I said. I'm going to set my origin on the ground. I will set upwards as being Y. I'm going to say that photo 1 is where it was released. Photo 2 is when it reaches its peak. Photo 3 is what happens at 4 seconds. And photo 4 is what happens when it reaches the ground. Now, let's list all of the information that we know and all of the information that we have to find out. There are 3 distinct phases we're going to examine in this question. Photo 1 to photo 2, photo 1 to photo 3, and photo 1 to photo 4. There's a displacement in every one of these. There's an initial velocity, there's a final velocity, acceleration, and a time. Now, because in all of these cases, this ball is under the influence of only gravity, the acceleration will be negative 9.81 for each one of these different cases. But we are being asked for different things. The first question was asking what is the maximum height? So that's really a masked way of asking what is the displacement between 1 and 2. We know that the initial velocity at 1 is 10 meters per second because that was the velocity of the hot air balloon. So in all of these cases, in fact, the initial velocity is 10. But from 1 to 2, we see it's reached its peak at the final point. And whenever something reaches its peak, that means that its vertical velocity is 0. So for 1 to 2, we know the initial velocity, we know the final velocity, we know the acceleration, we're looking for the displacement. What about from 1 to 3? From 1 to 3, we don't know the distance, or rather the displacement, we don't know the final velocity, we're looking for those two, but we are told that 4 seconds have elapsed from when it was let go to when it reaches this point. So the time is known. And finally, from 1 to 4, what we know is that the ball has started from its initial location and it's just about to strike the ground. That means that it has covered this entire distance from its initial position to the ground, which we were told was 300 meters, or more correctly, it's fallen by 300 meters, so its displacement is negative 300. And we were looking for the time in this case. So, we just need to go through this question step by step. Let's look at 1 to 2. We have the 2 velocities, we have an acceleration, we're looking for a displacement. there's only one equation that weaves all of those together, and that is toolbox equation number 4. Let's plug in what we know. Final velocity, 0, minus initial velocity, 10, is equal to 2 times negative 9.81 times delta y. Okay, so 0 squared minus 10 squared would give us negative 100, is equal to 2 times negative 9.81, which is negative 19.62, times delta y. So delta y is equal to 100 divided by 19.62, which is 5.09, or very close to 5.1. So that means that the displacement between photo 1 and photo 2 is 5.1 j hat meters, which also means that the maximum height of our ball was 300 plus 5.1, or 305.1. What about for 1 to 3? Well, from 1 to 3, we have the initial velocity, the acceleration, and the time. And we're looking for final velocity and displacement. So here's how I'm going to do it. I'm going to go with equation 1 to find out the final velocity. Toolbox equation 1 says AT is equal to V final minus V initial. So A, negative 9.81, times time, 4, is equal to V final, unknown, minus V initial, which was 10. So we can solve this as 10 plus negative 9.81 times 4, which is negative 29.24. And this would be in meters per second. Now that we've solved for V final, negative 29.24, we can solve for the displacement from 1 to 3. So from 1 to 3, we know the initial velocity, the acceleration, the time. We're looking for the displacement. Toolbox equation 2 will solve that for us. So delta y is equal to V initial times t plus 1/2 a t squared. So delta y, we do not yet know, is equal to V initial, 10, times time, 4, plus 1/2 times a, which is negative 9.81, times t squared, which was 4 squared. That should be a 4. There. Now, simplifying all of this, we get delta y is equal to 10 times 4 is 40, plus half times 4 squared, that would give us, 4 squared is 16, half of that is 8. So, let's try solving this out. 0.5 times negative 9.81 times 4 squared is negative 78.48. So delta y is equal to negative 38.48. And finally, to find the time from 1 to 4. So the way that we would do that is delta y is equal to v initial times t plus 1/2 at squared. Delta y is negative 300 is equal to v initial 10 times t, unknown, plus half acceleration, negative 9.81, times t squared. So simplifying this quadratic equation, we would get negative 4.905 t squared plus 10t plus 300 is equal to 0, and we would need to find the value of t. This would now be solved using the quadratic formula. So time would be equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a, which equals negative 10 plus or minus the square root of 10 squared minus 4 times a, negative 4.905, times c, which is 300, all divided by 2 times a. So let's simplify this. Negative 10 plus or minus 10 squared minus 4 times a, negative 4.905, times c, 300, is 5986. And the square root of that is 77.37. So all divided by 2 times negative 4.905 is negative 9.81. Now, if I added these two together, then I'd get a positive in the top and a negative in the bottom. But that's not a suitable answer because we can't have a negative time. So instead I have to subtract these two. That'll give me negative 87.37 divided by negative 9.81, which we could solve like this. Here's positive, just there, negative 87.37 divided by negative 9.81 gives us 8.97. No, 8.91. 8.91 seconds. That is the time that it takes for the ball to strike the earth.